Good morning, good afternoon, good evening, depending on where you are. We're very pleased to have this panel to focus on aerospace materials development, the trends and technologies pushing it. So let me start with do a brief introduction, a 1-minute introduction of each. Then we do 30 minutes of free flowing. We have some topics in mind, and I welcome you to key in your questions because we're going to leave the last 10 minutes for Q&A. So why don't we do 1 minute max, Ben, and then Hans, and then Dan?
Okay, sounds good. Thanks very much for the intro, Tuan. So my name is Ben Ferrar. I'm the Vice President of Carpenter Additive. I joined Carpenter Technology through the acquisition of a company called LPW Technology, a manufacturer of materials and also lifecycle management solutions for metal AM. My background is almost completely in metal additives. So prior to working with LPW Technology, I was in charge of R&D for Renishaw in terms of actual design of additive metals platforms. And prior to that, I did applications development for Stryker Orthopedics. So I'm really excited to be on the panel today and talk a bit about our material developments and a bit about our life cycle management technologies as well.
Thanks, Dan. Hans?
Yeah, so I'm Jonathon Hollahon, or most people in the AM community know me as Hans, but with Arkema as a business development engineer for our high performance polymers group. So with my products we work with focus heavily on aerospace, with a lot of the higher performing polymers. And then previously I was with Exact Metal on the laser powder bed fusion additive side of things. Was there for a number of years. Mechanical engineer by background, but find myself working more with materials constantly.
Thanks. Dan?
Yeah, I'm Dan Recht. I lead business development for Formlabs. So Formlabs is a polymer additive company focused on scalable machines, both laser sintering and stereolithography. My background is in materials engineering, but at Formlabs, I lead the group of people that works with our customers to push the boundaries of what's possible with polymer additive manufacturing. So doing things like custom material development, custom application development, and in general, trying to target products as opposed to prototypes.
Thanks, Dan. My name is Tuan Tranpham. I love 3D printing. I've been in 3D printing for 18 years, spent the first 10 in plastic, polymer, Z-Corp 3D system, object stratasys, and then spent the following 6 years in metals, which is relevant for aerospace. Is I spent time with Swedish Arkema, electron beam, which is now GE Additive, and then I joined a small startup called Desktop Metal in 2016, and oh boy, that was a ride. And between plastic and metal, I wanted to learn more about composites. So I joined Arevo about a year ago as Chief Revenue Officer. So for this panel talk to focus on aerospace, a little bit of outer space and drones and so forth, we often hear about materials as mainly composites or metals or polymer. But my first question for this panel is more relating to, is it, what has it been and what has changed? Is it been manufacturers are able to make the supply chain that is more a push to the market, this is available, take it or leave it? Or do we see a pull now from the market and they're saying, well, we actually know AM now, but we actually need these exotic materials and you need to find a way to enable us to get access to those. So this push and pull, anyone want to take on that?
I don't mind kicking off from the metal side. So I guess, it's a good question, right? Because we are seeing a transition within our industry where people are now starting to venture out further than the standard well-known additive materials. So like in metals, the 718, 625, nickel alloys, and your stainless steels 316. The typical materials that the printer manufacturers offer with the machine and offer some level of parameters, we're starting to see, especially aerospace customers, having developed, a base data set for those types of materials. And now they're really saying, okay, now what can we do to push the boundaries, right? What can we do to get higher temperature performance, or what can we do to really get a full spectrum of alloys that we would be able to use for other manufacturing methods. And the real key that comes with that is that the complexity isn't just in being able to make a powder material, or being able to print a fully dense component or a crack-free component. You have to think about all of the downstream processes as well. So we've done a lot of projects over the last year, 18 months on developing heat treatment processes, to make sure that you're getting a homogeneous microstructure in those materials, because they're the real things, or they're the real challenges now that the machines are getting to a level that they can reproduce fully dense structures.
Yeah, I can add a little, from the polymer side. I think a lot of the pull that we see from aerospace is the engineers and designers want to make sure they have familiar materials. So they want to use something that's on their material spec. It's a shorter barrier to entry if they can use something that's already being used in some other manufacturing format on their aircraft, but they have that material spec. So they like to lean towards that and away from, any proprietary blends that, they can't get the detailed information on. A huge frustration is, just tell me what it is, because I need to qualify it for my aircraft. So, I think there's a trend towards familiar materials, and engineers in aerospace companies really want to see that.
Yeah, we see that a lot at Formlabs, right? It drives aerospace companies to want to adopt our laser sintering platform instead of our stereolithography platform, because the laser sintering platform gives you that familiar nylon 12 material. But actually, on the stereolithography side, we are seeing some aerospace firms, and especially defense firms, starting to really trust the mechanical properties and asking us more and more for electrical properties and other material properties like temperature resistance, where the fact that we can meet the mechanical spec is starting to be taken for granted, and we're getting asked about some of the more arcane requirements.
Great. If we look at the more popular materials in aerospace, polymer, composites, and metals, and always about lightweighting and a bit more performance, do you guys see a shift in the ratio being adopted? Do we see both a rise in metals and composite? Do we see a rise in all of them? Or do you see any changes in the shift of the different material available? Has it not shifted a lot?
Go ahead.
No, go for it, Dan. You go for it.
Yeah, industry-wide, right, you see a shift towards composites. And I have a lot of personal experience with this. I was actually running a company that manufactured composites prior to joining Formlabs, and it was just very, very clear that the metal to composite shift was well on its way, even back 5 years ago. But I think what's really interesting is that then drives some interesting new polymer opportunities, especially in integrating those composite parts with the rest of the aircraft. That you have these complicated forms made of carbon fiber composite, and you want to mate those to metal parts, mate those to other composite parts. So you need really complicated polymer shapes. And that, I think, is creating an interesting opportunity for polymer additive as well to go alongside it. So I would say metal is always going to be really significant, but it's shrinking, and composite is growing, and then composite is creating opportunities for polymer. The polymer is never going to be the main driving material on the aircraft.
Yeah, I would echo what Dan said, right? We saw Boeing go from an aluminum body to a composite body. So the trend, in lightweighting, in the broad sense of the aircraft, I think, is definitely, we see the trend from metals to composites. And maybe the big question is, okay, well, polymers versus composites, where's the play there? I think something interesting that the AM community needs to watch for is this kind of trend in how can we move away from one-time use thermosets that are cured, and then once they're cured, that's it, and move towards thermoplastics, which can be repaired, can be welded, to other thermoplastic parts. It opens up more flexibility on processing options. You can reduce cycle time. So I think the AM community, especially around composites, needs to look at, from thermosets to thermoplastics and where the industry is looking in that sense. Because, when we look at sustainability, cycle times, there's a lot of benefits to the thermoplastics. And that plays right into the AM community's hand.
Yeah, I think I can talk within the metal spectrum, right? And if we were to go back 5 years, we would have seen, heavy dominance in an aerospace R&D perspective from, titanium and aluminium, like believing that they can really see those lightweighting benefits by adopting those materials. What we're starting to see now is more confidence in the technology, so people can look at more critical applications. So moving to more of the sort of functional or the super alloy type materials for high temperature, we're seeing a lot of growth there. And also, going back to the new materials aspect, we're seeing much more grades become more standard across the materials that we supply and the parts that we print internally.
I agree with you guys. I see the same. If you up the plane in two pieces, the engines and the fuselage, I see a lot more composite, a lot more polymer growing. But for the high temperature, the low pressure turbine blade is going even beyond Type 6.4. So I think it's material temperature melting point where it will find its niche and the adaptation of that. I think what I'm trying to go next is in terms of pushing for more materials development. Do you guys see that? So historically, the OEM in aerospace do their own due diligence, but sometimes seek the supply chain, tier 1, tier 2, or the knowledgeable service bureau like Morris in the past, or Ingodema, or more 3D, doing some due diligence with them because they might not have enough talent. Do you guys see now that they are bringing it in-house, or are they still leveraging the supply chain to push and drive and enable more materials development? So the question is the supply chain that is doing the work for more materials, or is it still ODM doing it together,
And it's certainly the case at Formlabs that we've done materials development projects with some of the tier 1s in the aerospace industry as opposed to the OEMs, where they've said we have a particular material need, whether it's for our investment casting or some of our more complicated fabrication processes, for essentially a supporting material, something that's going to let them create a composite or metals part through one of these processes that's able to give you a good super alloy at the end. So I would say there's appetite for materials development, both at the OEM level and also at the tier 1 level.
Yeah, I think a lot of that drive comes from ultimately the OEM, but a lot of the workload ends up being on the, I look at, Dan and Formlabs, they're one step ahead of us as the resin supplier. So, our material is already qualified. It's flying on aircraft, but not via AM. So a lot of that legwork and push has to come from the AM machine manufacturer to demonstrate that their process can match the expectations that they get with other processes. So for us, I think the ultimate pull comes from the OEM wanting to be able to use the material in other formats or use new materials. But a lot of that legwork gets done via I'll call it the machine manufacturer, or in some cases, maybe with metals, it's more who's doing the actual processing of the material, where a lot of that qualification legwork gets done.
Yeah, I completely agree with that, Hans. I mean, when you think about the number of alloys and materials in the metal space that are used in the aerospace industry, at Carpenter Technology, we're so fortunate that we've got 130 years of that materials data, and there's a huge number of those materials that we've just never tried in additive, but have really good applicability in terms of weldability to be used in the process. So whilst we're interested in developing new materials, we're also able to move some of our existing portfolio that are traditional raw products, right, and use them over in additive, and use the knowledge and the databases that we have around materials. One of the things that I would say is the biggest challenge in this area is getting repeatable properties as the materials are used, right? So it's all well and good having good properties from a virgin batch of material. But as it's recycled throughout the process, and as you're trying to qualify that powder or that material, how is it changing over time? How do you refresh the material? How do you top up the batches in the material? And we're seeing so many different strategies from different end users that it means that data doesn't necessarily translate in the same way from one application to the next. So it's really important for customers to be able to, have the traceability and be able to, collect their data in a manner that means it can be mined correctly and used correctly.
Yeah, I mean, just pulling back the curtain on something we did at Formlabs, right? When we were developing our Fuse 1 system, the selective laser sintering machine, we did so much engineering work on just figuring out what the top-up rate for powder was going to be for that machine, that we wanted that to be minimized, right? We want to maximize the amount of powder you can recycle while getting material property within spec. And I think, like, looking back, it's one of the biggest engineering challenges we had. And now, like, that the machine is in the world, we are still finding that customers top up at whatever rate they want.
Yeah, because it's 3D printing, right? I mean, if your ink cartridge runs out on your printer, you just put a new ink cartridge in. You just fill it up and expect the same property, expect the same printout on your paper over and over again, right?
Yeah, but I mean, they're driving their costs up that way, right? I'd much rather them take 70% used powder and use a 30% top-up rate, because we think you get, as far as we can tell, the same properties that way versus virgin powder.
I mean, it becomes that big question, right, of risk of running the machine over a long build time and have one build fail versus knowing when your end of life is exactly and being able to throw out the powder and start again with confidence that you're not creating waste. It's such a trade-off.
Yeah, and it's interesting that, like, polymer sintering versus metal sintering really fall at different places on that, because the metal powder and the metal builds are just so much more valuable per build than the polymer powder and the polymer builds.
Yeah, that's a good point.
Yeah.
So if pushing more development for materials, and if 3D printing is roughly hardware, software, materials, and the process to go to mass production with documentation and so forth, what are the three challenges that is lacking behind? For instance, there is a material that you can do in additive, but maybe even meet all the spec and the standard, let's say Type 64, but the economics does not work. That is still so pricey because the machine is expensive or limited supply chain. What do you guys think are the top three challenges for even more materials to be adopted in the industry?
Yeah, I think if you think about Type 64, right, and there's a critical issue with the material when the yield is this, right, and for of metal powder, for example, and we use this in our laser systems, and we use this size, a larger size fraction in our EBM machines or other types of additive platform. Now, the reality of it is today is that we use two different materials, two different grades. They're still Type 64, but you want grade 5 for the EBM type cut, and you want grade 23, the lowest oxygen content possible for the laser cut. So that causes a discrepancy, right? You're using the full range, but not of every heat of every batch. So one of the things that we've worked on developing is developing an alloy where you can tune, where you can get the same properties or improved properties for both of those segments, but using one material. And that's a material we call grade 23 plus. So that still sits within the normal ASTM specifications for Type 64, but by really controlling both the interstitials and the other elements in it, we can enable us to get better properties for both of those fractions of material. And as you said, right, it's critical for the adoption to get the full utilization from an economic perspective. So,
I want to say the P word, right? Post-processing is like such an economic driver for 3D printing. Like, when I think about what I tell our R&D teams at Formlabs, it's always, can we reduce the customer's labor cost? That's that's 100% where my mind is these days. And it's everything from, can we make it easier to remove the support material? Can we make it easier to set up and configure prints? And this is, across every platform we have, every material. And I think it's something that as an industry we need to face, across every material system, metal and polymer.
Yeah, I agreed. I think, there's still a cost element, right? We haven't gotten rid of that. And getting a process that is reliable enough to be qualified in an aerospace application is still not a trivial endeavor by any means, even, with some of the best equipment. And so the cost involved in doing that is still a barrier. As far as, when we look at hurdles for new materials, I feel that there's still a desire to see the current materials used more. I think when we look at, the current available materials and think, okay, we could probably take these into more applications than they are today. And I think there's still maybe not quite that level of historical confidence in a 3D printed PA12 part versus some, molded plastic part that's been used for 30 years, 40 years. So I think there's still a growing confidence level in the current materials that'll be available. And as we see them become adopted more, that in turn drives the effort to qualify new materials and experimental materials, going outside of the normal bounds. And that's maybe speaking from the polymer side a little bit, but I would imagine in metal, we're still not at the confidence level of a 3D printed titanium piece. Even if we've done a lot of testing, we still don't have that same level of confidence as a machined piece that's been used for decades and decades.
And exactly the same thing applies, right? So, we may have a customer who has been making a part for 30 years out of 304 stainless, right? And they come to additive manufacturing and they want to make it out of 304 because if they're changing process, they want to keep the materials the same. But they could have a superior material like 316, for example, and because of the economies of scale, even though in a wrought form it's more expensive as a material, in a powder form it's actually works out less expensive because of the volumes it's being produced for the industry, right? It's the same. It's exactly the same thing with grade 5 titanium versus grade 23 titanium. Right, there's more produced of grade 23, so it's typically a lower cost material in powder form. But because you're not doing custom heats, you're not making specific materials, right? You're using what is typically produced and available. So I think it's something. I think you hit the nail on the head, Hans, when you said it. Right, is encouraging people to use some of the standard material or more standard materials is a good way to go to drive the economics as an industry.
Okay. It's my assumption that that hardware equipment could be more reliable, could be more stable, and maybe they can be a little bit faster. And maybe we are waiting for other technologies with higher throughput without compromising quality. To enable more materials, Dan touched on, maybe we also need to focus on reducing the post-processing. But I want to talk about software a little bit, because I think what's going on in the industry, and I want to hear your thoughts on this, is the software. Will more machine have software with eyes and brains, meaning machine learning AI, and have vision and collect the data, especially for FAA parts that you need documentation and so forth? What are your guys' thoughts on the software? What can be done better that will enable more materials development in aerospace?
I think, I think there's nothing's going to change on the qualification end. I think we're still a long ways off from maybe reducing the amount of testing required to certify a material based on machine learning and computing. I think the FAA is, and companies are still going to want the same test results, pull X number of tensile bars, CT this many parts, but I think software can help us get there faster. So I think where the software can come in is reducing the number of times you have to iterate to dial a material in, and hopefully it gets you much faster to the point where very quickly you can jump right into printing, tensile bars to go into qualification testing and test samples to submit for qualification. So I think, when we look at machine learning, there's huge opportunity there to reduce the time around process optimization and jump right into the qualification, or not right into, but jump quicker into the qualification. I think ideally, being able to certify parts based off of machine learning data and in situ monitoring would be the dream, right? But I think we're a long ways off from having that degree of confidence to begin to substitute the rigorous destructive and non-destructive testing that has to be done to qualify a part.
Yeah, and
go ahead.
I was just going to follow on from that point to say part of the challenge today, right, is we have a process with a huge number of variables and almost discrete buckets where data is held, right? So your material certification information will be held in one software system, your machine process information will be held in another software system, your design data is somewhere else, and your post-processing information is somewhere else. And the reality of it is with these processes, unless we can link up all of the data out of those systems to enable us to get to the AI, you may be seeing some changes over here, and you may falsely recognize it as because of a change of variable on the machine, but it could have been something to do with feedstock, or it could have been something to do with post-processing. So AI is brilliant, right? I mean, it enables us to process so many more variables than the human brain can imagine, right? But if you're not taking all of those variables into the same database and not providing it as a key data set, then you're going to be missing out on, or you're going to be making false assumptions throughout those processes. So I'd like to see more consolidation and more data sharing across platforms. We're still as a part of an industry where people are holding pieces of data, within their machine or within their post-processing as their data bank, right? And until we can get that cross-functional sharing, we're really not going to be able to realize the benefits that we want to realize from, the digital technologies.
Yeah, I mean, that cross-process data sharing is really important. It's what's driven us at Formlabs to try to own every step of it, right? To write our own software, to make the machines, to formulate and manufacture the materials, to make our own post-processing equipment, just so we can deliver so much more to the user and so much more reliability by having all of those things talk to each other. And so when I look at having, spent years working with that kind of integrated data, what I find is that there's still just a ton of low-hanging fruit. Just in our preform software that we write, right? I remember when we added, okay, don't let the user put the support right on the corner of the part. Warn them. Do basic things like that are going to make you more successful, save you a ton of time and money, are still up for grabs. But there's a role for machine learning to play down the road, but I think we have so much more space for human intelligence to just make the software usable and cost saving.
Yeah, that's a great point, Ben, because the challenge in aerospace, if there is a problem, right, is where's the problem? And when you look at this complicated value chain of, okay, we're a resin supplier. Now those resin pellets go to somebody who makes it into filament. That filament gets sold to somebody who prints it on their machine, and then somebody's post-processing that part, doing support removal, surface finishing, and then it goes to an end use. And so when it fails, track it without a cohesive, data tracking of that process, finding where it went wrong. Did we mess up on the batch? Was the viscosity wrong? Did the filamentizer undersize or oversize the filament? Did the printer malfunction? So that's a really great point. I think, being on one end of the value chain, getting visibility across the whole process from start to finish, I think is really important as far as gaining confidence around being able to identify, problems along the process.
Especially when these processes are still so susceptible to outside characteristics, right? I mean, so we have customers working in production with aluminium, for example, and they really struggle from a humidity perspective at certain times of year, depending on where they are in the world, right? I mean, there's a whole load of those types of things that mean that we need to capture more data, and we need to, make sure that that data is validatable, right? Or validated information.
Another topic I want to bring up is in this economic financial situation we're in with COVID, do you guys see a change in behavior from the OEMs in aerospace? Are they doubling down, being more adventurous, creative, spending money in materials development, or you haven't seen a change?
I would say we see a lot. Recently, it seems on the DoD side, there's heavy interest in clearing up potential global supply chain issues, and maybe that's because they have a little more cash at their disposal in the current situation. But I think aerospace companies are evaluating their mindset on how they do that. I think, frankly, not to be a downer on the situation, but a lot of them are looking at, okay, we just need to survive this right now and be able to come out stronger on the other side of it, and aren't necessarily in a position to make capital expenditures in the current climate. But I think the mentality is there of, hey, this kind of supply chain disruption can be catastrophic, and looking at domestic sourcing, flexible sourcing, in-house, parts on demand. I think that's all aspects of it. But I think they do need a little time to rebound and start proactively moving on those ideas.
Yeah, I mean, in my experience, over the past year, I've seen still strong innovation initiatives on the defense side, but it's been pretty quiet on the civilian side. I think those folks have, at least with our machines, kind of retrenched to prototyping, to kind of working on core revenue generating projects, and not so much on new materials, new applications. But I want to second what Hans said of, like, on the defense side, it's really open season on innovation. There's lots of very cool stuff happening.
Absolutely.
And hopefully that trickles into the rest of the industry.
Yeah, I totally agree with the comments of Dan and Hans. I mean, what we've seen is where on the commercial side, right, is we've seen where people may have been very protective over IP or their own projects previously. We're seeing more collaboration. There's a significant cost to qualifying a material for aerospace, and I think people are realizing that, look, to step forward together and share some of that risk at the front end is going to be helpful for an industry as a whole. So more subcontracting and more partnering to develop new materials and to develop materials data.
I think we're right on time. So let's leave the last 10 minutes for Q&A that we have. The first question that got the most votes is, how is the industry interest for ceramic or ceramic composites material? What do you guys see?
You picked the one material that's not, I would say, representative here on the panel. I can't speak as much to the ceramics 3D printing side of it, but when you look at ceramics and ceramic composites, I would say that the current buzz in the industry is around hypersonics. There's recently been a big push in hypersonics, and I think you see a lot of the ceramics and ceramic composites coming into play in those super high temp applications. When you're dealing with temperatures of over 1,000 degrees Fahrenheit doing Mach 5, I think that's right now where the buzz is around really high temp materials like ceramics and ceramic composites.
I would also just pull us back to like the original use for aerospace ceramics, right? The thermal barrier coatings, and those are deposition processes typically, but additive is playing a bigger and bigger role in the tooling, the fixturing, the masking for those processes. That as the barrier coatings get more expensive, as the geometries get more complicated, we're finding that we are selling actually huge amounts of printers and materials into masking for that operation.
I agree with you guys. I'm actually in continuous carbon fiber. We've seen the trend from thermoset to thermoplastic. I don't hear much about ceramics. Maybe the volume, the size, the equipment is not as big, and therefore is not touched upon as much. The next question relates to new materials. We keep talking about new material like carbon fiber or glass composites will replace metals, and whether we'll see much investments in metal powder. Let me take that one first. Carbon fiber has been used for actually a long time. It's how you define additive manufacturing, because AFP, the fuselage, the body, has been done by 3D printing. It was just huge, $3 million 6-axis robot arm doing very wide tape. So, and the wings as well. So that is kind of 3D printing already. What we've seen currently in the industry is miniaturizing that, doing a 1 meter built and 1 meter cube built envelope like Arevo. So thermoplastic is happening, but I think for the economics that I touched on, just because you can do it doesn't mean the industry will adopt it. There has to be economic, financial justification, and I think the machine needs to be faster for them to actually take it to mass production. Any other thoughts on that?
I think, the question phrased mentioned something about we seeing investment in metal powders. I think we're not going to see a slowdown in investment in metal powders. I think maybe like we touched on a little bit earlier when you talk about hot parts of the jet engine, your composite from a temperature standpoint is only as good as your matrix. So you can have a super high strength thermoplastic composite, but it's still going to be limited to that temperature limit of the thermoplastic matrix, or else you're going to start melting the material. So I don't think the composites are going to replace these metal parts where that temperature is a factor. If it's going to 500 degrees C or more in an engine, unless we make massive strides on the thermoplastic side, I don't think we're going to be replacing some of these high temp titanium parts purely on a temperature basis. Where we see the composites and where Tuan hinted is, like an aircraft fuselage on a normal subsonic aircraft. It's not going to see super high temperatures, so the strength is the key factor, and the composites can make a great play there. When it's temperature, your composite is only going to be as good as the materials that compose it from a temperature standpoint. So I don't think we're going to see a slowdown in metals as we start, as they hone in on these parts that have to be metal.
Yeah, I agree. I think that there are different applications, and there's a place for both of those types of technologies. I think the key here is that we're talking about additive today being able to solve a whole load of different challenges, whereas maybe a decade ago there would be one or two. Now there's applications all over an aircraft which can be solved in all different materials. So it really boosts the value proposition for companies making investments in these types of technologies.
Yeah, I mean, the applications really do come out of the woodwork. We recently released a material that's a highly glass-filled composite. We call it rigid 10K. 10K is the modulus in megapascals. And what's interesting is it immediately got picked up for hypersonic wind tunnel testing. And you don't think of wind tunnel testing as something where you have strict mechanical property requirements, but at the loads when they're doing hypersonic testing, you actually need a super strong composite material that you can print.
Another good question relates to metals. What are, in your opinion, the top 3 metals being used by aerospace today?
Nickel alloys, titanium alloys, and aluminium alloys. I don't think we can really dissect it into much more detail than that, because there's different applications. For example, within the nickel alloy space, we see a huge amount of 718 for things like either gas conveyance or hydraulics. We see a huge amount of 625 in the hypersonics type area, and so I think across those material groups, there's definitely the number 1 or number 2 in each of those areas, but people are still people are still widely using a full range of products to find solutions, or materials to find solutions.
Good. Another question relates to that composite material can actually be used safely and be robust enough for aerospace. I would say inside the body, when it's non-flight critical, like the aluminum bracket underneath the passenger seats, whether that needs to be done in metals or composite, I think those where composite 3D printing thermoplastic is today, I think it will find applications given the size. Inside the fuselage is where I would see composite materials starting to try to expand applications.
Yeah, I think composites in general have been used for a long time, and the thermosets certainly have a great history in aerospace, and there's a lot of confidence there. The question now is, thermoplastics, and okay, how do we begin that qualification stage? I think absolutely the thermoplastics can be used in applications where you can use thermosets. I think the bridge to build is the qualification and the history. Thermosets have such a long history in aerospace. There's a very high degree of confidence. The thermoplastics are somewhat newer, and I would echo what you said, Tuan, is, start with the lower criticality and move from there, and then continue trying to expand the applications.
And it's also that aerospace is bigger in terms of breadth than it used to be, right? We've got UAVs, we've got commercial space flight. There's a lot of places where you can be introducing new materials and new techniques. So it's not just, where on an aircraft, but also very broadly, what kind of aircraft we're even talking about.
Yeah, that's a great point, Dan. When we look at the UAM, UAV market, that's really where a lot of the buzz is around thermoplastics and looking at actually using them as primary structures for the aircraft. Now, a lot of the UAM urban air mobility companies are starting with a thermoset material because of its history, and there's a shorter path to qualifying an actual vehicle. But when you look at the volumes that these companies want to do, the traditional processes just aren't going to cut it. When you talk to automotive companies who are investing in this and startups, some of the well-known ones like Joby or Archer, when you really want to look at the volumes they want to do, thermoplastics are the way they're going to have to go, and there's just going to have to be a bridge to build there in terms of qualification.
So besides the plane, what other verticals excites you? From my side, I agree with you, especially delivery drones or eVTOL like Ilium in Germany. Those are exciting new verticals that expand besides the commercial planes. What other verticals excites you these days that could be driving materials development?
I'm excited by alternative powertrains for aircraft. And I think electric and hydrogen-powered aircraft are a really interesting space. I mean, granted, they're not going to replace fossil fuel-powered aviation for quite a while, but they have really different challenges in terms of how they're running their engines, how the forces and stresses are distributed from the engine motion, what kind of flight patterns they're going to have. And it creates a lot of opportunity also for lightweighting because they don't necessarily get to carry excess fuel for those durations.
Excellent. Thank you so much for your time, and we hope that the audience found some insights in this panel talk. I want to thank you all for your time spent here. Thank you.
Thanks for having us, Tuan.
Yes, thanks for moderating, Tuan.
Yeah, thank you, Tuan. And thanks to the audience.